Hello and welcome to another lecture Administration of Operating Systems course. Today I will be talking about some of the common and useful servers that you can set up on the Linux system. So SSH, FTP, NFS and Samba are the examples of things that we will talk about. Now we will start with Telnet. Telnet is a very basic protocol which was originally developed for access command line interface, and there are a number of session options that basically show this kind of heritage. But since it does not provide any kind of data encryption, and that means that usernames and passwords are being sent over the network in clear text, which is obviously very bad, it's very rarely used for remote access anymore. Sometimes it's still used in specialized circumstances, for example, for accessing Azure embedded devices, or if you know that you are in a secure environment, for example on home or local network, you sometimes can use it, but in general that's not what you want to be doing. And here is an example which shows why. You can see in here a session that was captured using a Wireshark tool, which is a commonly used tool for that kind of purpose. And the setup was that there were two computers that were communicating using a Telnet protocol, and a third computer which was eavesdropping on this conversation. As you know, the Ethernet network protocol is a broadcast protocol, so it's reasonably easy to listen to all the traffic if you know what to do. So in this case, we have a number of TCP data packets belonging to the Telnet protocol, to this particular one Telnet session. And if you examine those packets one by one, you can see that first server asks about the login data, then the client sends the username, server asks about password, and client sends the password. Now, in this particular case, obviously the data is fake, so there isn't anything terribly wrong here, but in general, you can easily see that if this was a real communication, it would be really easy for an attacker to get access to sensitive information. So this is something you really want to avoid in real cases. Now, Telnet is still commonly used as an interactive raw TCP session. So basically the idea is that if you want to send some particular information over TCP, Telnet is what you are typically using to do it. Now this is not strictly correct. There are a couple of minor differences between what Telnet protocol actually sends and what you type in the command line. There is, for example, a special character which allows you to do various out-of-band communication and advanced features like that. But this particular case is not very often encountered, so in practice it works pretty well most of the time. Now there are some specialized raw TCP clients, but they are not very commonly used. If this is something that you are going to be using very often, then you can investigate it, but most of the time Telnet is perfectly fine. So the idea is that you can use Telnet to fake a lot of different protocols. So HTTP, IRC, POP3, SMTP, all those protocols, basically large part of them at least is just open text communication, and those parts can be pretty easily faked using Telnet. Now, for example, FTP actually does use the same data format. So here is an example of using Telnet, and in this particular case, we are actually faking FTP protocol. So we are connecting on port 21. Here is some general information from the Telnet, and then here is the session, what server sent, the response from the client, another response from the server, client, server, and so on. Typical interactive communication, and it ends with just closing the connection by the server after the client has done the quit command. So if you want to actually use this kind of remote access to command line interface, you want to be using probably the SSH protocol, which stands for Secure Shell, which allows you to access remote systems, but it does encryption of all the traffic. It also provides host verification so that you can avoid so-called man-in-the-middle attack when you are connecting to not to the host that you want to be connecting, but to somebody else who then forwards all the traffic, but gets access to it and can eavesdrop on it. The SSH uses asymmetric key encryption, which I will talk a little bit about in a second. And the client is installed by default on virtually every GNU Linux system. However, SSHD, which is the server part of it, can be installed by hand, and you use the standard command to do it. There are also SSH clients for all the common systems, and one of the more popular ones is the PuTTY for Windows. So this is the one you will be using during the labs, for example. Within the SSH suite, there is a number of tools. So there is the SSH itself for remote shell, there is the server, there is a tool for copying files, there is an interactive file transfer protocol, there is a utility for creating the key pairs, and there is an agent for storing and accessing passwords and passphrases in a secure way. So here are some examples of how those commands can be used, but the SSH is only as secure as the users who are using it. So if you are thinking about what's the basic security ideas behind SSH, the most important one by far is to make sure that your users are using reasonable passwords. This particular point is way more important than all the rest taken together. If the passwords of your users are not secure, then neither of the other approaches will do anything particularly useful. So in general, it's a good idea to establish public key-based authentication. So instead of using passwords to log in, you want to be using public and private key pairs. Now this is more complicated to set up, so not all users can be convinced to be doing it, but in general it's almost always a good idea. The obvious thing is to disable remote login for root. Now you are in general supposed to have the root account disabled so that nobody can log into it, but even if you don't, you almost certainly don't want to have root available as a remote access account. You may want to change root for SSH daemon, so for example lock down users just to their home directories. You really want to do something about thwarting brute force attacks, so you want to make sure that, for example, delays between subsequent connections is big enough and things like that. You want to make sure that you are using protocol second version of SSH protocol. There are some security vulnerabilities in SSH version 1. It's most of the time on by default, but you want to make sure that this is the only version that's possible. And then one common thing which does a little bit, but not as much as people like to think, is to change the default port from 2020 to something else. And the question of is it worth it and what you actually achieve by doing that is kind of open and not necessarily clear. Now, when I talked about encryption, the most obvious case of encryption is so-called symmetric encryption. When you have two users, Alice and Bob, and they both know some kind of secret key, so they share a little bit of secret knowledge, and that key is unknown to the Eve. So this is what you typically call the eavesdropper. Now, having this kind of shared secret knowledge allows Alice and Bob to communicate in such a way that Eve cannot understand this communication, using a lot of typical and some pretty obvious schemes. Now, in general, the problem in this kind of approach is you have to distribute those encryption keys somehow in a secure way among peers who have never interacted before and who can only communicate through the network, which is inherently non-secure. So in the internet setup, that doesn't seem to be reasonable requirements. Now, historically, you would have keys that were agreed upon personally, so you would meet once and then you could communicate forever. But, well, internet doesn't quite work like this. So one useful thing to do is to find out some way of establishing a secret without actually meeting. And one example, quite simplified, it's not exactly how it's being done nowadays, but it's a general idea which is intuitively clear, is that Alice sends Bob a number of unique puzzles. Now, each puzzle has a name, and there is a lot of them. you need to have a huge number of those. And Bob chooses one of them at random, solves the chosen puzzle, and then sends Alice the solution. The tricky thing is that now both Bob and Alice know the secret, which is the name of the puzzle that Bob has chosen. Because if we assume that Alice knows answers to all those puzzles, and each of those answers is unique, then from the answer that Bob provided, Alice knows the name of the puzzle. And obviously Bob knows which puzzle he has selected as well. The interesting thing is that Eve does not know this name. Even though Eve was able to eavesdrop on all the communication between Bob and Alice, unless she was able to solve all the puzzles, and the idea is that the puzzles should be not very difficult to solve, but sufficiently difficult that solving all of them is not possible. Or the other thing for Eve to do is to try to guess Bob's random choice. Now this is why for cryptography the idea of being able to generate truly random numbers is very important, because if Eve can guess what Bob's random choice was, then she doesn't have to solve all the puzzles. She just has to solve the same one as Bob did. The other approach is to use something called asymmetric encryption, in which there is no need for a shared secret, but instead we use public and private keys. And the idea is to, first of all, have two different functions, one for encryption and one for decryption, such that if you encrypt your text using the public key and then you decrypt it using the private key, you end up with the original text. And it's also, in practice, turns out that most of the schemes allow you to do it in the opposite order as well, which is useful, but less crucial. And the main requirement here is that it's difficult to deduce the private key, even if you know the public key. Now, having this kind of scheme allows us to make the public key available to everybody, so that everybody can encrypt a message using public key, but then only Alice, only the person who knows the private key, will be able to decrypt it. So then if Bob sends encrypted message using this kind of scheme, Eve cannot decrypt it, even though she has had access to all the communication between Bob and Alice. Now, it's not entirely obvious that this kind of scheme exists, but it turns out that it does. There are some mathematics in which we will not get into, but there are a number of schemes which fulfill those kinds of conditions, which actually allow this kind of communication to occur. And this kind of scheme is used by SSH. So there is a file called known hosts for each individual user, as well as the global for the whole server. And this kind of file, first of all, lists all known remote hosts, as well as their public keys. And the idea is that when you first connect to a particular host, SSH on itself cannot, of course, verify the identity of this host, because why? There is no way for a computer program to know that you have connected to the server that you wanted to connect to. However, after the first identification is done, SSH will remember the public key for a given host, and afterwards it will be able to verify that it is actually talking to the same remote system as before. And it will then warn the user if something is wrong. Now, there are some valid reasons for key change, but there aren't many of them. So for most, especially for servers to which you are supposed to be connecting via SSH, those SSH private keys should remain constant. So whenever your SSH client warns you about the change of the key, you should take it seriously and figure out if there is a valid reason for this to be changed. Most often not, and so you can try to figure out what's wrong. And the other area where you can use asymmetric encryption is, instead of inputting password every time you try to log in, you can authorize using asymmetric cryptography. So as a user, you generate a personal pair of keys, which one is public, one is private. And you put public key on the server. So the public key, as the name suggests, is something that you can make available to everybody. There is no risk involved in it. Now you have to keep the private key safe. You typically protect it with a passphrase anyway. And then you want to tell the server that everybody who knows this private key is considered trusted. So you are using the key instead of the password. And it's significantly better than a password. And you can use SSH-I or SSH agent to actually do it. And this kind of information you put in authorized keys file, which is a list of public keys for authentication. And you can basically specify that all the connections that can authenticate using corresponding private keys will be accepted without passwords. There are a couple of different key formats depending on your server, client, and so on, but typically you can figure out ways for having those communicate. Also, in the same file, you can specify some additional options. For example, you can disable X11 forwarding, or you can automatically execute commands when somebody logs in using this particular public key and so on, which can be useful in some situations. I have talked about X Windows system before a little bit, but it's interesting to come back to it now because it was from the very beginning designed to be network-based. So it allows you to access the graphical user interface over the network transparently for both the user and the applications. And the X server process communicates with client applications. On one hand, it passes the user commands to a particular application, and on the other hand, it performs requested graphical operations so that the user can see them. Now, this kind of scheme also allows any single X client to be a server for another application, allowing something called X nesting. So you can have within one application a window that belongs to another one, but that's more advanced topic. Now, the general overview is something like this. You have X server on a particular machine, and you can have a number of applications, so-called X clients. Some of them can be on the same machine, but some of them can be on another machine. And this X server is connected to user's workstation, and you have keyboard, mouse, and screen. Now, the problem with this approach is that the original X11 protocol does not use any kind of data encryption, so it's really easy to eavesdrop on this traffic. And therefore, Secure Shell allows you to set up something called X11 forwarding, where the goal is to allow remote system to display graphical user objects on user's local machine, but we want all this traffic to be encrypted. And in order for this to work, you obviously need X server on the local machine as well, because there must be something on your local system that knows how to display things and understands all the commands. Now, but the SSH daemon actually acts as the X server or remote hosts. So all the graphical user interface applications connect to this kind of fake or proxy X server, and all this traffic is tunneled over encrypted connection, and then the SSH client acts as the graphical user interface client to that server and displays all the graphical user interface objects of the remote applications. So if you want to set up something like this, first of all, you need to find a local X server. If your local machine is a Linux system, then it's pretty easy. If it's, for example, Windows systems, there are some free implementations of X server that you can be using. Then you connect to GNU Linux system, for example, using SSH. You define an environment variable called display, for example, specifying your IP address. And then you can start any kind of graphical user interface application, for example, Firefox, which will display the window locally. Now, this will work assuming X server accepted the connection from the remote system directly. This one was not tunneled. And in general, by default, it should not. Most servers are configured in such a way that they will not allow external connections due to security reasons. As I said, the traffic is not encrypted. So what you really want to be doing is you want to enable X11 forwarding in your SSH session. So for example, you can use SSH-X instead of just using SSH. And then the server on the remote machine will create a process that emulates the X server. And by default, it will define some particular display variable, which will refer to the local host. And then the data will be securely transmitted over the network, and the SSH client will operate as X client, relaying all this information from the remote system to the local X server. And this kind of mechanism can be used for forwarding any kind of traffic. It doesn't have to be X11 traffic, it can be anything. And it's commonly used for securing protocols that are otherwise unencrypted. So for example, POP3, SMTP, IRTS, those kind of protocols. And you can have local port forwarding, where you are opening new ports on the local machine and they are transparently forwarded to the remote machine. Or you can have remote port forwarding, where you are opening ports on the remote machine and all the traffic is transmitted to your local machine. If you look at the configuration of SSH daemon, there is a number of options that you can look into, and some of them you will play with a little bit during the labs. I will not go into details here, but of course all the documentation is available. Now, you should more or less know it, but just to go over the process of installing a new service. So for example, if you want to install the SSH server, the first step is to find the package. So you can do it by looking at the documentation. Google knows a lot of packages. There is a community of Linux users that can probably give you advice about what kind of package will solve the problem that you currently have and so on. Then you obviously have to install this software. And then it's very often a good idea to review the configuration. And sometimes you also have to remove the so-called safety lock. So a lot of configurations come with something that disables them, basically. So if you try to run a service with default configuration, it will just not do anything. And the idea is to force users to actually review the configuration adapted to their particular setup, and only after that is done to allow starting the service. Now, it's often a reasonable idea to first start a server like SSHD just as a command line utility, because it allows you to get more immediate feedback. If you start the server as a daemon, the way it's supposed to be started in the final setup, then you will not be able to communicate with it. You will not get any kind of output on standard on your screen. You will have to check the logs in order to find out if something went wrong. You will have to figure out which logs to check and so on. And a lot of the servers you can just start normally from the command line, and then instead of putting all the information in the logs, they will just display it on the screen, which makes it easier to figure out what's wrong. Then you have to verify that it's working, and well, also working as intended, so not just doesn't crash, but also allows you to do the things that you want to be doing. And if it's working fine, then you want to set it up as a daemon. So, for example, to be started every time you reboot the computer on a particular run level, and so on. So as I said, when you want to execute the server, one option is to do it as a standalone, just a regular application started from a shell. And this is also something that you typically can do as a regular user. So if you don't have root access to a particular machine, but you want to test some configuration, make sure that it does what you want before you ask the administrator to set it up for everybody, then this is very often a reasonable idea. Now, if you really want to install it as a service, then one way of doing this is to look into the etc initd directory, which basically contains shell scripts which are executed at boot time which start and stop various daemons, both automatically whenever you are starting and stopping computer, or actually changing between run levels, but they also can be done by hand. So all those scripts in the directory can be executed by hand. So for example, after you change configuration or when you want to temporarily stop a particular service, you can use those scripts to do this. So for example, there is once you have installed the SSHD daemon, you can use this kind of command to check the status if it's running or not. Now, Ubuntu actually comes with a more modern replacement for inetd, which is called Upstart, which is an asynchronous event-based system. With general idea is pretty similar, except that instead of using scripts in etc initd, you are using the service command, and then you specify which service you are interested in and what to do with this particular service. An alternative way of doing things, because both initd and Upstart basically say that, well, this is a service that should be running all the time whenever the computer is on. But there is also a different mechanism which is called inetd, and the idea is that this is a so-called super server. So this is a server which listens on a number of commonly used ports and only starts appropriate daemon when that daemon is needed. So inetd would be listening on, for example, port 22, and when connection arrives, only then will it start the SSHD server. So there is some security improvement with this, there is some memory usage improvement with this, there is a little bit latency because then whenever a new connection arrives, you have to actually start the server as opposed to have it already running. So there is a trade-off that you may look into. Here is an example of configuration script for Upstart. This is for SSH server, and it contains some reasonable information like description on which run levels to start and stop this service. Then it should be respawned automatically within some reasonable limits, and some additional information. The pre-start script, for example, which basically checks if all the preconditions for starting this service are fulfilled before it tries to do it, and so on. I have also already talked about change root, but again, change root is particularly important for different services. You want to make sure that those services have as little permissions as possible, so you want to make sure that they can do what they have to do, but not significantly more. So change root is designed to prevent processes from accessing files outside of what they are supposed to be accessing. And well, since those locations cannot be named, there is no way to get to them. And this works for process children, obviously, because it wouldn't be particularly useful otherwise. But it's important to know that this is not intended to defend against root. So if you already have root permissions, then you can break out of change root jail. So that's something to keep in mind. The other protocol I wanted to talk about is FTP, which is file transfer protocol. And as the name suggests, it's used for transferring files to and from remote host. And here is an example of how an FTP session might look like. And you may notice all the information, all the lines that come from the server, they have some information in text, but they all start with a particular number. And the idea is that this is kind of a service that you really want to be able to create tools for making it more intuitive and natural to interact with. So you don't necessarily want all these interactions to be done on command line, but in order to do this, you need to have a way for those tools to understand server responses. And this is where those codes come in. So those codes all have 3 digits, and the first digit is the most general description of what's actually happening. So there are 6 of those in standard FTP. So first one is positive preliminary reply. So this reply suggests that everything is fine, but it's just preliminary. The operation is not yet finished, so this is the first step. Then there is positive completion reply, so this basically means that whatever the user requested has been successfully done. Then there is positive intermediate reply, there is transient negative completion reply and permanent negative completion reply. So as the name suggests, the idea is that this one, something didn't work, but if you try again, things might change. And this one means that, well, what you wanted to do didn't work, and it's not going to work any better if you try again, unless you have changed anything, of course. And the second digit is more specific what is the idea. So you can be syntax, information, connection, authentication and accounting, and so on. And here is some example of actual responses, and so you can think about how they map to those groupings that we have talked about before. But the general idea is that if you are designing a client for FTP, for example, you can look at those numbers, and if you understand the protocol, based on those numbers, you can provide users with appropriate choices. So for example, when uploading a file didn't work, you can give them an option to retry if it was the transient error, but there is not much point in giving them option to reply if the server says that, well, for example, they don't have permissions to download this file. There is not much. Just retrying again will not fix this issue, so there is not that much benefit to trying it. The one interesting thing about FTP is that you actually have two different connections in this protocol. So we have so-called control connection, which this is the connection over which you have the interactive part of the protocol. So we are supposed to send several commands and receive several replies within one session. So we connect once, and then you keep sending commands until you are done. And this kind of connection typically starts with authorization. So you have to, for example, before you can create a directory, you often have to log in with a user or password. And there is another connection, so-called data connection, over which you are sending and receiving the actual data. So both file upload and download, as well as actually directory listing, this goes over the data connection. So there are two ways of initiating data connection. There is active mode and passive mode. The active mode is the original one. This is how the protocol was originally designed. The problem is that this active mode requires that server is able to connect to the client as well for sending data. And this doesn't really scale that well. There are firewalls problems with this kind of thing. There are network address translation problems with this kind of approach. So at some point, a passive mode was introduced, which allows the client to keep connecting to the server all the time. So client doesn't have to be accessible from the server. And there are some interesting design ideas behind having two different connections. Now there are some problems with this, of course. It's more difficult to program, and it's quite difficult for firewalls, for example, and also in general it's not very network friendly. But there is a number of features that wouldn't be possible if you only had one single connections, but they are made possible by those two connections. And the original FTP protocol is very old. So if you read the RFC for it, RFC stands for request for comments, and this is a typical format in which open internet standards are created. You can Google for FTP RFC. If you find the original one and try to read it, it's actually pretty funny. It, for example, predates the time when the 8-bit became the common format, so it talks about how to talk to computers which are using 6 or 7-bit format. But it also means that since the original design, there is a number of extensions to the protocol which allow you to do some useful things, like, for example, data encryption. which allow you to download and upload parts of the file, which do different kinds of date manipulation or language and character encoding, which allow you to specify some site-specific commands. So you can basically, it allows every server to extend the FTP protocol in whatever way they want. So nowadays you are mostly using FTP either in web browsers or for accessing public data, for example, for downloading free software repositories. If you want to install OpenSSH server, for example, there is no drawback in using unsecure protocol like FTP because the data is public anyway. If you don't want to be downloading data, if you want to be using remote file system in a more transparent way, you can be using something like, for example, network file system. And this originates from the 80s. It was created first by Sun Microsystems, and it uses client-server architecture in order to export part of file system hierarchy and to mount remote file systems. And the idea is to present standard Unix file system interface in order to be transparent for both users and applications. And you want to have access to remote files, which would allow you to do all the normal operations. So you want to list contents of the directory, you want to read file, write some data into file, delete, and so on. Now there is a trade-off between complexity, features, efficiency, and reliability. All those things have to be taken into account when designing this kind of system. So for example, there are issues with proper handling of concurrency. If you have multiple clients accessing the same data, you have to be able to provide some kind of guarantees about locking, about who wins with concurrent writes, how to solve read-write race conditions, and so on. There is also a problem of handling dropped connections gracefully, because most applications actually expect disk writes to be reliable. If you have an application which knows that it's communicating over the network, there are typically different kinds of safety measures built into it, because the application expects this network to sometimes not be available, for example. But if the application is just writing to the disk, then it's very common that it assumes this kind of access to be reliable. But if this actually is transparently communicated over the network, then all those problems with network connections can appear as well. And in general, if you think about how to access remote data, there are two major types of service. So you can think about upload-download model, which is what FTP was all about, where you basically start by copying the file from server to client. You then operate on it locally, and then you copy it back to the server. Now, this method is kind of simple, but it's first of all potentially wasteful, because you don't necessarily need the whole file. Maybe you just need part of it. And also it can be inconsistent, because if multiple clients download some version of the data, both clients change it and then both upload it to the server, there is no mediation that will make sure that the data isn't lost. One of those modifications are very likely to be lost. So the other approach is the remote access model, where there is some file service which provides an interface that allows you to do all the basic operations that you want to be doing. And then clients can only get the necessary data. They don't have to download the whole file. There is a server which has a coherent view of the file system. But network problems become tricky to handle. In the upload-download model, it's really easy. You try to copy a file from server to client. If there is a network problem, you don't get the file. It's obvious to everybody. If you try to copy file from client to server and there is a network problem, also you know something went wrong. You know what the current state of things is. Now, If you have a remote access model, it can be tricky to figure out exactly what has already been done, at what point of the network transmission the problem appeared, and so on. So, from NFS point of view, there is some number of design goals which they try to solve. So first of all, they want single machine to be both a client and a server. And this also includes circular dependencies, which is kind of interesting. It was crucial to support diskless workstation. That was the main idea. The Sun Microsystems wanted to have a setup in which you could have workstations without any actual data. All the data was supposed to be provided over the network. They wanted to support heterogeneous networks with different hardware, different operating systems, and also provide users and applications with as much transparency as possible. So in particular, they wanted to support all file system calls. So all the operations that kernel provides on a local file system, they wanted to provide on the network file system. And in order to provide some recovery from the failure, the protocol was completely stateless. And when something didn't work, client would just retry the attempts. And for that reason, it used the UDP protocol. The idea was to have high performance, so they used client-side caching and server-side read-ahead. They had very limited consistency guarantees. So if multiple clients tried to access the same data and especially modify it, that was not as good as on real physical disk. There were some trade-offs. This wasn't considered a particularly important point, at least initially. There was no support for data migration, so you couldn't move resources from places. There was no data replication. And there was also basically no file access semantics, so no file locking, no reference counting, and the security model was also very basic. So some of the things, or from some of the aspects of the NFS were actually pretty advanced, but some of the things were a bit simplified. So here's an example of architecture, how it looks like. You have a client and a server, and on the client side you have your user, which has some kind of file system interface, and those can be different kinds of interfaces. So the most typical one is the one with the actual physical disk, but there are other file system types like prots, FS, and so on. And one of those is also an FS client. But again, there is some file system interface provided by the kernel, which is common for all those different kinds of data. And then for NFS client, the data is actually transmitted over the network from NFS server. And on the NFS server, it works in a very similar way. There is a common file system interface, which the server accesses, for example, when it wants to read data from a physical disk. If you want to install the client and server, it's a pretty standard procedure. It's important in this context to know about the mount idea. You already know that in the Linux and other Unix-based systems, there is a single root for the whole file system. Now, since this is regardless of actual number of physical disks, each device has to be mounted in a particular place. So if you, for example, have 3 different hard drives, you have to tell the system before the data can be accessed where in the file system hierarchy should this particular data be located. And you are using the mount command to do it. So you specify the device and you specify in which place should it be mounted. And you do it the same way for all different kind of resources, so for hard drives, CD-ROMs, and also for network resources. And you do it in a file called etc fstab. You can also provide a number of mount parameters, so you can mount a file system as a read-only or read-write. You can allow or disable execution of files from this file system and so on. But in general, the original NFS protocol, it operated over UDP because it was slightly faster than TCP, especially for the local area network. Now, modern versions actually use TCP because it's better suited for wide area network setting. And also the initial implementation was fully stateless, so that client and server crashes were relatively harmless. They did not disturb the other side. They would just retry the access, and for example, if server crashed, the client would keep retrying the access. Once server came back online, the server didn't need to remember anything about the previous request from this client. So each new request could be fulfilled without any kind of temporary data from the past. So server, once it came back after the crash, would be able to serve the client just as well as before. So again, NFS server defines a so-called virtual file system, so it does not really manage the local disk layout. It uses remote procedure call so that the programmers can ignore the network protocols. It's the kernel that actually sends requests to the server and awaits the responses. And it's also important to remember that NFS server uses so-called trusted host security paradigm. So it just checks the IP address of the computer that's making the request in order to verify if it should serve the data or not. So again, as long as the kernel on the client side makes the proper verification of the users, that's fine. But if the remote host becomes compromised, then this kind of security paradigm doesn't really hold. So it's not necessarily very good in modern days. Now, from client's perspective, the first thing that happens is the so-called mounting, where the client sends a particular path name to the server and requests permission to access the content. And then server returns so-called file handle, which contains some number, but the general idea is that this file handle is persistent. It's calculated based on target inode, and so every time a client requests access to a particular path name, server will return the same file handle. And again, the idea is that if the server crashes, the file handle that the client has will still be valid after the reboot. It's also interesting to think about how file access protocol over NFS is different from the local file access protocol. So when the client performs this preliminary lookup remote procedure call and gets back file handle and the attributes, there is no information which is stored on a server. So this is a lot different than the local open operation, where the kernel actually stores a lot of information about the file, about the current position, about the permissions, and so on. And so in all the future access functions, this kind of handle is used. And there is also pretty complicated cache validation scheme. There is pretty complicated file locking scheme for making sure that you can ensure, for example, atomic operations on files and so on. The data caching on client side is mostly designed for efficiency, so you don't want to be sending the data over network every time the client needs to access the data, but you also need to ensure some kind of cache consistency. And in NFS, you can achieve so-called close to open cache consistency. So you make sure that if client A closes the file, then its content is synchronized with the server. Not every time when A modifies the file, but only when it says, basically, now I'm done. Those are all the modifications that I care about. This is the time when the timestamp is changed. And then when the client B opens the file, it will check that the local timestamp agrees with server timestamp. And if not, it will discard its local cached copy. So the idea is that if client A closes the file before client B opens it, then the data will be consistent. But if both clients open the data at the same time, or client B opens the data before client B closes it, then there are no guarantees that client B will see the changes that client A introduced, for example. Now, the typical usage of NFS are pretty clear. So you can have roaming home directories, for example. So for user convenience, all the machines on the network might have the same home directory for the user. You can use it for data sharing. So for user cooperation, several users might want to work on the same data. You can use it for application export. So for saving both space and administration overhead, you can install applications once and then have all the machines on the network being able to access those applications and use them. You can have diskless systems, so you don't have to equip your workstations in actual physical hard drives, thus saving some costs, and also allowing net boot, so you can boot from the network without anything. Alternatively, you can have a dataless system, so basically a system on which all the operating system data is on a physical disk, but no user data is on local machines. All the user data is on a central server, which basically simplifies configuration and upgrading of those machines. Still, there is a number of trade-offs within NFS. I have talked about some of them, but the big issue is that a single volume can only be managed by a single server. So you can have high loads, but it simplifies the concurrency protocols. Now, for typical usage, those that I talked about before, it's perfectly fine, but there is a lot of other remote file systems for different possible use cases. So remote file system, Samba, Andrew file system, Google file system, WebDAV. Those are all examples of systems that on some abstract level do exactly the same thing as NFS, just in a slightly different way. And early NFS systems had a number of potential problems. Modern systems are significantly better. Most of those have been addressed. There is also a Windows client for NFS, which is part of so-called Windows Services for Unix, which is an implementation of user mode POSIX subsystem. So it's not kernel emulation, it's all in the user mode, but it contains a number of things that are almost complete POSIX subsystem. And especially together with NFS, a useful utility or feature is the auto mounter, because the idea is that classic mount is a little bit cumbersome. It can extend boot time extensively. It can be painful to administer on a larger scale when you have multiple systems which rely on each other and where you then have to make sure that they are booting in appropriate order. So auto mounter allows you to mount file systems on demand. Only when local directory is referenced, the operating system will send a message to a server and try to mount it. And in this particular case, you can actually have multiple servers and then first reply wins. So you can have some very crude load balancing solution. And here are the obvious commands for installing and configuring auto mounter. Now, another way of accessing files remotely is to use a tool called Samba, which is the free implementation of SMB CIFS protocol. So this is file and print services for Microsoft Windows clients. And the idea is that in general, as I said, there exist NFS clients for Windows, but it's typically much easier for Linux to pretend to be Windows than to get Windows to admit that Linux exists. And also Samba allows you to share more than just files. You can share printers, serial ports, and so on. If you are just thinking purely about files, the NFS is actually a better protocol. In practice, for the situations for which you would be using those, it typically doesn't matter. But there are some benefits on a protocol level of NFS over SMB. Now, on the labs, you will be using Samba configuration file to set up a communication between virtual machine and the Windows host. So smb.conf is a file you will be interested in. It's actually a pretty complex file. It's large. It consists of a number of different sections. And within each section, you have a number of different parameters that you are interested in. They typically come in this kind of format. You have name and then a value. And there is a lot of different options within Samba, and some number of them have pretty complex dependencies. So there is also a utility called testparm, which will check your configuration file and tell you if there are any obvious problems with it. If it doesn't complain, it doesn't necessarily mean that the configuration file will do what you want it to do, but at least you can be reasonably sure that there are no syntax errors and no obvious inconsistencies within the file. So there is a number of things that you should think about when you are configuring Samba. So you can specify a guest account, so user who will be able to access data without authorization. You also can specify IP-based address security, so which hosts are allowed and denied access. You can send passwords either clear or encrypted, depending both on the Samba configuration and on the version of the client on the Windows side. You can specify which users can and cannot access particular resources. So actually the security model for Samba is pretty complicated. You also can specify username map. So you can map usernames from the Windows side to usernames on the Linux side. It doesn't have to be one-to-one mapping. You can have multiple users on Windows side mapped to a single user on the Linux side, or vice versa, depending on what kind of security model you are looking for. And Samba uses NetBIOS, but I will not go into this particularly here. The more interesting thing is that Samba actually consists of a number of different utilities. And some of them are the servers that you have to be running in order to take advantage of it. And then there is a number of client applications for doing different kind of things. There are some utilities that help you configure Samba and so on. The security model, as I said, is reasonably complex. So the idea is that you can use username and password for authentication, and you can either use Samba's own list of user and password pairs, or you can use a number of standard solutions like LDAP, Network Information Server, and so on. Now, with modern versions of Windows, passwords are usually sent encrypted, but there are some older versions that used clear text. And it's important that whenever you expect a particular user to be able to use Samba, you need to use Samba password tool to assign a particular password to a particular user, because some passwords used within Samba are not necessarily the same as the ones used to access the actual Linux account. And as I said, on the labs, the idea is to use the configuration file for Samba directly, but you don't really have to do it in general. There are a number of tools that allow you to do configuration. So one very simple one is called Shares Admin, which is a graphical user interface which looks kind of like this, and it allows you to set up some very basic information, and then you can just add some number of users, some number of shares, and specify for each folder some very basic properties. And if you want to do more than that, there is also a utility called SWAT, which is actually a web-based solution, which is pretty easy to use, generates good configurations. The big benefit is that it has very extensive help system, so you can get a description of every available option. And it actually, especially in the advanced view, allows you to modify almost everything. Almost everything you can do directly in the configuration file, you can also do within SWAT. Now, SWAT used to require to enable root password, and I actually think the book still claims that it does, but it's not entirely true. You can now use SWAT without doing such a bad thing. And here is an example of initial page for SWAT. All those buttons and all those links here will take you to particular parts of the configuration file. Finally, I would suggest you take a look here where Andrew Trigel, the actual author of Samba, has a very interesting course about free and open source software, and in particular there is one lecture specifically about Samba as a case study for the course. And I think the whole course is very interesting, but especially this one lecture is definitely worth seeing. So thank you very much, and I will see you on the lecture.